Hello and welcome. My name is Frank Fischer, and this is the content that I wanted to show during a roadshow in the UK, Ireland, and Poland. But as of Corona, I'm not able to do this, so we had to postpone the Java user group tour. I will for sure do it with updated content. But for now, this is the content that I wanted to show, and here we have it as a video. I will add a lot of more, so to say, background information. I add some more demos that I hadn't had the chance to show during the other times when I presented this content. So it might be a bit more lengthy. Maybe it gets 1.5 hours or so, but there's more content in there. And if you want to jump over things, you know how to operate YouTube, I think. So I can leave this to you. Okay, so let's get started. The topic of today will be practical static program analysis or static code analysis. In the academic world, it's more called program analysis. I think in the rest of the developer world, it's called program analysis. But in a way, it's the same thing. My name is Frank Fischer, and this is my Twitter handle. If you want to ask questions, update anything, just use a private direct message on Twitter, or have a look at my Twitter channel anyways. Good. Without any ado, get into it. Maybe a bit background on us. So we are DeepCode, as you can see, a team of roughly like 20 people. DeepCode was founded in 2016. It is a spin-off of the local Zurich University, ETH, the Eidgenössische Technische Hochschule. And it's a deep tech startup. So it's based literally on like a decade of research in the field of static program analysis. And as you will see later, we are using a mixture of different AI mechanisms to use AI to help us set up the system and make it run. You see the people jumping in the picture, so this is us. Maybe a few words about me. I'm Frank Fischer. I'm like forever in IT, feels like 30 years now or something like this. I used to work for large companies like Microsoft, Google, Deutsche Telekom, but I also worked for startups in smaller environments, always IT related. From an academic background, I have a master in IT, I have a master's in physics, and I'm currently doing my master's in organizational psychology, but that is not done yet, so I'm not claiming that I have it already. Okay, so that should set the stage a bit. You will see more about DeepCode, our offerings, and the differentiation and stuff like this later in this talk. What will we cover today? I would like to start with an intro, some statistics, some motivations, some stuff that should make you frightened, so that you have a motivation to look on the rest. And for the rest, we will start off with a theory refresher to lay some groundwork, so that you see, how these things are, what are the topics that I am about to talk about. So semantic versus syntax, machine learning, symbolic AI, representing code in graphs, so stuff like this we will talk about. And then we get into the different static program analysis tools, from like the lowest complexity going up the ladder to higher and higher complexity levels. So textual things, linters and abstract syntax trees, the event graph, symbolic AI that we start. And then I would like to get very practical in things. So the do's and don'ts on building your own tool stack and using the tools. And in the end, some outlook. Where is the whole industry heading currently? What are the things you can expect as a developer happen in this year, maybe next year, from the industry? And last but not least, call to action. I would like you to go out and change some things or start some things so that you actually get something out of that talk here. Okay, so that is our agenda. Let's get into it. Starting off with a motivator, and I think the easiest motivator that I can think of was actually this. I saw this message here on Bloomberg. It's about one of the probably most expensive defense projects ever taken by the US. It's the F-35, and you can see it's riddled with software issues. In this article, they talked about 873 software issues. I saw somewhere that they are actually accumulating more issues per day as they can actually solve. And this is a huge problem, obviously. I mean, it is one of the largest projects they ever did, and it's riddled with software quality issues. So I think we all understand what is behind the scenes happening there. I could add more examples. We could talk about the Boeing thing. We could talk about the Israelis losing their moon probe and a lot of other things. So software issues, software flaws are all over the place. I digged a bit deeper and I found some numbers, and the consortium of IT software quality, or for IT software quality, made a study for the year 2018, and they estimated that in the year 2018, in the US alone, we had the cost of poor software quality in the US alone, 2018, was approximately 2.84 trillion US dollars. To give you a perspective on the number, I printed out the numbers and all of the zeros on the lower side of that slide here. This is roughly the GDP of the UK. So this is roughly 10% of the GDP of the USA. This is an enormous number. I was surprised, to be honest, about the size of it. So it's a problem. It's a problem not only for the software development community, it's a problem for, I would say, society in that regard. So we need to do something about it. If you look into what the consortium, so to say, in the bar chart, not the bar chart, in the pie chart, actually, so to say, lays out as the typical sources of these problems. You see like 37 something percent is software failures. You see that there is a lot of technical debt and legacy system problems. I would say probably the same thing in a way. You see that finding and fixing the defects is actually also a majority cost driver. So knowing about a fact is not enough. You have to find and fix it. And this is a huge cost driver. So we're talking about substantial amounts of money here. And I think that is a reason to kind of dig deeper and think about that. If we are talking about software quality, we're talking about this. There's an ISO standard, 25010, that describes what is software quality. And they are making these categories: functional suitability, performance efficiency, compatibility, usability, reliability, security, maintainability, and portability. And some headlines per these divisions here. The ones that are marked yellow, in my perspective, are the ones that are very directly related to software engineering. We can say that usability, this is kind of a different, a different field in a way. It's more psychology oriented, blah blah blah. But in a way, all of the others are like more of the majority are related to software engineering. We can argue now: is software engineering really engineering? I would say it's not. In an engineering field, you would be able to set up a product, to set up an outcome in a way that you can guarantee that it works. If you're building a house, you're making a plan, and the plan is guaranteed to work. If you're building a ship, the ship is guaranteed to stay afloat. We are not in that situation in software development currently. Software engineering is more based on the let's try and test approach than any other engineering capability. So in my perspective, maybe we should not call it software engineering, but let's stick with the name. Software engineering. So these are the aspects we have to cover. These are the aspects we have to do. So now, as developers, as the guys who do the software, who produce these software, what are the implications for us? And there are some like typical tool sets, typical best practices that we should have a look at. The first one that is quite interesting is the relative cost of a bug. So what does it cost us to clear out, to get rid of a bug in software. And as you can see, in this graph here, it's kind of getting exponentially higher the more down the road we are with our project. And this is based on research from NASA. It's based on a study done by IBM. And the outcome out of this is that the further down the road we are with our software project and we discover a software bug, the more expensive it is to address this bug and to clear out the bug. And this is kind of true if you're using Agile. Then you do the same thing in a 2-week cadence. It's probably even more extreme if you're doing a waterfallish process model. But in a way, it holds water for both of these project models. So the earlier we can catch a bug, the better it is. Because as you can imagine, if we are in the most extreme situation, in my model here, the customer facing bug, our bug is literally leaked to the customer. We're not only suffering trust issues with the customer, and we probably lose customers about this. We are also in a situation that we are now getting back probably very fuzzy feedback from the customer telling us about a probable bug. We have to set up the environment accordingly. We have to find out what was the cause of that bug. So that's a lot of research work, a lot of detective work to find that out. Then we need to find the reasons within the code. Then we need to address that. Then we change it. It goes through the code review process. It needs to be deployed. There needs to be the automatic testing, the manual testing. We have to go through the whole process cycle again to get this deployed, which means a time delay, but it also means a lot of costs that are acquiring. Another thing that you can read out of this is you would like to have your quality elements, your quality assurance elements that you have here. You want to have them set on top of each other, and you want to have the more complex situations later down the road. So as an example, the manual testing you have, you don't want to block your manual testers by finding a very low complexity bug after 5 minutes of testing it, maybe blocking the rest of the day for the manual testers, because now they cannot proceed with the testing test cases. You would like to have your manual testers to find complex bugs in complex scenarios, scenarios that are economically not automatable. You don't want to find them that they cannot log in because the login text box doesn't work anymore. You would like them to find very complex cases within your software. So that is the point that I wanted to make here. The more we get down the road, the more complex and the less error cases you should have. You should automate as much as possible and as much as economically sensible. And obviously, there's a kind of a movement in the industry currently. It's called the shift left, pushing the quality assurance, the leftmost, economically sensible leftmost in this setup of activities that you have here. Okay, so from this, now let's follow the blue pointer to the right. What are the things we're doing as software developers? We are using revision control, and I have the aspect and typical applications, typical solutions you're using. So revision control, Git is obviously, I would say, the market leader currently. We're doing testing. There's unit testing, there's integration testing, penetration testing. So we're doing testing, we're doing code reviews, we have the pull requests, and there are some tools around that. We do static analysis, and this will be the focus of today. How does this work? What kind of tools are there, and how should these tools be looked at? And last but not least, we're also doing instrumentation, monitoring, the DevOps idea that there is no more separation between the development and the operational side of it. And there Java is the Lang instrument, for example. For us today, we're looking now at this yellow circle, the static analysis. And when we're talking about static analysis, this means we're talking about the analysis of the application looking from the source code without actually running it. So a static analysis means analyzing software without actually running it. In contrast to dynamic program analysis, where we actually run the software, run test cases, put it in special environments and stuff like this. Static analysis can work in a situation where the software is not able to compile, for example. You can do static analysis when it's not complete. In the very, very early stage of your software development, no environment needed to be there and stuff like this. So this is static analysis versus dynamic analysis. And this is our topic today, static analysis, that we want to look at. Okay, so static analysis is actually not super new. The first linter, I think it was 1975 or so when the first linter came to the market. And it's around for ever since. And so you would say, okay, it's a kind of a given. Everybody probably uses static analysis as of today. Actually, not quite so. There is a survey, again, 2018 was this survey done. It's in the Java virtual machine ecosystem. So it's a Java related survey. And as you can see, there are a lot of people using tools. There are some market leaders there. There's a PMD, for example, which is an open source tool. The shocking part about this is 36% said they are not using a tool at all. This is something I would like to address with this presentation here. We need to change this. There's no good reason not to use static program analysis in your tool chain. Another aspect of this survey was the security tools. So there are some static program analysis that are focusing on security, some are like more broad. And as you can see, again, security tool, 72% says do not use a security tool. Oof, yeah. I think that is something we need to change this. Okay, there is no good excuse not to do it. When we are looking later down the tool stack, down what different tools are there and what tools should I use as a developer, I would like to make you aware of some aspects of like the challenges that this field of program analysis, despite its age, still has and is still coping with. And maybe some of the fields are now like, and this is a breakthrough we see currently happening, some of the fields are now addressed that we will see in the outlook and stuff like this. Okay, what fields do we have? Today's limitations. Performance is a limitation, and you will see that code is very complex. And if you are transforming code into intermediate representations that you need to kind of unlock it for the static analysis, performance becomes an issue because complexity goes exponentially. The amount of memory you need, the amount of CPU cycles you need is enormous. So performance is something that you want to look at. There is no need in a static program analysis tool that takes weeks to come back. It needs to be in a way from a performance perspective fast enough to fit into your work cycle. There are some quality aspects to static program analysis. Recall gives the amount of suggestions that come out of your scan. The precision is how many false positives you have versus true positives versus real bugs that were found. A false positive is a bug that was shown by the system, shown by the static analysis, but is not a bug in reality. What kind of types of bugs do you have? Some of the systems are looking into security. Some of them are looking more broadly. Style is kind of reviewed and stuff like this. So these are quality aspects. Polyglot. I think I can argue that today you don't have a single language project anymore. You have JavaScript in there. You have maybe some Python scripts for deployment and stuff. So there is a huge mixture of things, and that the tool needs to adapt to that. It also needs to speak some of these other languages, so to say. Linear scaling of rules is a big problem, and the reason behind that is, as you will see, we have a lot of rule sets, and these rules need to be done by something or someone. And as of now, it is developers doing this. So you need to have highly specialized, highly trained developers doing these rules. And obviously, these developers are scaling linear. A developer can do what a developer can do a day. The more of the rules you want, the more developers you need. And obviously, developers are in short supply, as you can imagine. Expressiveness. When you have such a tool, the tool is only helpful if what comes out of the tool is actually has like 3 aspects to it. So number 1, as a developer, I need to understand what is the problem here. What does the tool want to tell me that I have to address here? And I need to be quickly able to understand and grasp what's behind it. Number 2, there's always the situation that you have false positives. So the second thing is I want to now see if this is a real problem in my code or if I see a false positive here, which might happen. And number 3 is now I need to fix it. And how can I fix this? Is there a good idea on how to fix the issue that was presented to me? Is there something like a best practice I can simply apply in my case here? So that the bug goes away. So these are the 3 things that I want to see from a good tool, and I call this expressiveness. And that is also something that we need to see in these tools. Last but not least, API use. Today we have an enormous amount of new APIs, new libraries coming out every week. I mean, there's the running joke of the JavaScript community literally changing the underlying APIs they're using like weekly. But the point on this is it's a kind of a given in the whole industry. Think about C++ now coming out with version 20 of the C++ standard. A lot of new things in there, and I see not a lot of things being so to say used already from the later or from the earlier standards. They're still trying to catch up what was in the earlier standards. The same is true for all the libraries coming out for Android, for Java environments. There's a lot of change going on there. So why is this now interesting for the static program analysis? The point here is that these APIs are sources and sinks of data, for example. Okay, so you have an API call that might result in external incoming data that might not be clarified. The data might be malicious. There might be an attacker using this channel to feed data into your application, like injection problems, for example. And there might be a sink, this might be a new way of addressing your database. This might be a new way of addressing the file system or whatnot, So APIs are of a major interest, and they are ever changing. And if we now have a linear scaling of the rule sets with ever changing new upcoming APIs, this is a recipe for a lot of stress on the systems here. Okay, so have a watch out, have these things in your back head when we are moving forward now, and I will try to answer what the industry is actually doing about it when we are to the outlook and to what is kind of currently happening here. Okay, next refresher. Let's get some ideas refreshed in our minds. I think most of it you already know about, but I think it's good to cut them refreshed. Okay, so let's start with semantic versus syntax. Let me start with this little application, and I actually have it here in Visual Studio Code, and you see this application here. It's a class equal or not. You see it has a function called double p, and the double does nothing else than using the parameter that it gets xxxxx, adds these parameters up. And we're using this function here in our main function. We're calling p with .1, okay, 0.1. What you would expect is 0.1 plus 0.1 plus 0.1 should be 0.3, right? So we can say this should be equal to 0.3. And as you can tell by down here, it's actually not. So what we can do is we can run it just to show you that it's true what I say, and it says not the same. Why this? Yeah, because obviously what we have here is we have a rounding error. You know, this results not in 0.3, it results in 0.3000004. It's a rounding error that is in the Java virtual machine, and the result of it is that the behavior is not as we probably would expect it. So here we come to syntax versus semantics. From a syntax perspective, this is all good. You know, the Java compiler, as you have seen, there was no problem with the Java compiler. It is all valid Java. The point is now the semantic. Is the intent, the meaning that the developer brought into this, is this correct? And I would argue now, as a developer, it's a bad habit to compare two floating point numbers directly with this. You always need to have this epsilon distance, you know, this kind of a margin where you say within this margin I accept the floats to be equal. So the point here is, while it is syntactically correct, it's semantically maybe not correct. And this is something where we will see a lot of problems coming up from. Your static analysis should go into the semantic part of it. So your static analysis should argue by using rule sets that probably semantically you're not correct here. And by using the syntax versus semantic, you will see we can actually eliminate a lot of problems. So what are typical semantic issues in Java, for example, is implicit type conversion, precision, as we see here, operator overloading. There's a problem with synchronized on strings. I just did a blog article on that one. So there are lots of problems around this. The null pointer, you know, that you can have object reference being null, for example. So this is a problem when you have syntactically correct code, but semantically might not be correct. Okay, so this was refresher number 1. Refresher number 2. Trees. How can we represent code to unlock, to get into it and to find the patterns and stuff that we want to have? Well, we're using graphs in that, or trees in that regard. And the most prominent one is actually the abstract syntax tree. And literally every compiler uses this abstract syntax tree as a first step in getting into unlocking the code, so to say, to compile it into what should be executed later on. And the abstract syntax tree, I find some nice examples for that. For example, this one here. This is a JavaScript abstract syntax tree, and it's visualizing nicely the abstract syntax tree of this Java program here. And as you can see, the JavaScript program, this is the JavaScript program. It has 2 variables, it does an add and stuff like this. And what you have down here in this abstract syntax tree is the variable declaration. You know, you see it highlighted here. A becomes 42, and then let's go down a bit. B becomes 5, and then you have a run statement plus between A and B and stuff like this. So it's a nice visualization of what is happening, so to say, within the application that we have here. So this is the abstract syntax tree. There are other trees that have other aspects of the application that they kind of show. So for example, there's the control flow graph. Instead of the abstract syntax tree, which doesn't give you any information about the flow of the application through these elements of your application, the control flow graph shows you how the flow through the application looks like. So for example, if you are searching for dead code, you're searching for elements in your code that are never touched, the control flow graph can actually give you information about this. Because if an element in your application is never to be reached within the control flow graph, it's kind of obvious in the control flow graph. Within DeepCode, we are using another graph that is called event graph. And the event graph is literally taking the elements of your code and recording the events, the interaction between the elements in your code in a graph. And as you can see, this is a kind of an example on how this looks like. The event graph is very powerful because it kind of records the history, so it's flow sensitive in that regard. It records the interaction between the different elements, and we can learn by applying rules by using event graphs of applications, as we will see later on. So the point that I wanted to make here is there is the graph representation. Abstract syntax tree is probably the most prominent of them. There are different graphs that have different pros and cons. Some of them are flow sensitive, some context, path sensitivity. The point on these graphs is that they are also, there's a downside to them. You know, the richer they are, the more memory they need. The richer they are, the more time to generate they need. And obviously we need to make a good balance, a good trade-off in which kind of intermediate representation to use to get the information that we want to have, but on the other side also not going overboard performance-wise. So these are the, so to say, the aspects that I want to make you aware of regarding these intermediate representations code in graphs. Next one is a very prominent one these days, and it's artificial intelligence. There are two ways of doing artificial intelligence. There's a symbolic and a sub-symbolic way. And since artificial intelligence is currently like the thing, I would say, maybe we dive a bit deeper, and it's quite nice to have this kind of an information, the kind of a background on what is happening there. Okay, as you can see on the slide here on the right side, symbolic and sub-symbolic AI, this is kind of a heat map, you know, over the years on which field of AI was actually kind of hotter, you know. So the red one is the sub-symbolic one, and we will see what sub-symbolic means in a second. And you see both of them started roughly the same time. So the 50s, 60s, there was a lot of hype about it. And then sub-symbolic kind of crashed down because it needed a sufficient CPU performance and sufficient memory, and that was obviously in short supply during that time. But then it spiked again, and during this winter, where both AI categories were kind of under pressure, both of them suffered. But then you see here from the 20 to 2010, the sub-symbolic AI kind of peaked up, and you can literally argue that the AI hype that we see currently is based on the sub-symbolic part of it. But you also can see the symbolic one had quite a high time here during the 80s, beginning 90s, and then crashed down and is now below the sub-symbolic one. But currently, a lot of scholars argue that only the combination of both of them will actually result in what we want to achieve with AI. If we do not come back to symbolic AI, we will probably see another AI winter kicking in. Okay, so now, what is sub-symbolic AI? What is symbolic AI? And here in the middle, I have the sub-symbolic AI part, and it's literally machine learning. It's the methods you are using by using probabilistic algorithms. So you have training data, you're using machine learning infrastructure. You can see here the neural networks and support vector machines and, you know, the Bayes networks. So this is sub-symbolic AI. It's below symbolic because it is based on probabilistic aspects. Then you have on the other side, you have the symbolic part, and the symbolic part is based on symbols, on rules. You know, you're recording facts about the world, and then you're arguing over these facts, expert systems, you know, stuff like this. So this is symbolic AI versus sub-symbolic AI. There are pros and cons of both of them. And if you're looking at the different elements that there are, So symbolic AI, as I said, is based on rule set. It's based on programming the rules, on programming the facts about life. And then you are setting search algorithms over that. So you have your rule sets. You are talking about ontologies, which are like structures of information, plans, goals, stuff like this. It is very easy to debug in a way. It's very easy to explain why the argumentation is the argumentation is. Why does the system come back with this kind of a deduction out of it? It doesn't need to have any kind of big data. It is very easy to explain the thought process of people in that. It's like you can, it's easy explainable in that way, and it's better for abstract problems. The subsymbolic one, as it is machine learning, it has this Bayesian learning, it's deep learning, it's, neural networks, all of these things. It's very robust against noise, the subsymbolic one, where in contrast to the symbolic AI, that is, noise is a problem there. Things that are not fitting into the pre-coded knowledge set are kind of outside of it and hard to argue. It has a very good performance, the subsymbolic AI, especially nowadays by using the graphic card GPUs that we have. It doesn't need less knowledge on the field up front. We don't have to come up with ontologies like we probably have to do on the symbolic side to understand what is the field of knowledge that we want to capture here, to set up the elements that we want to see in that. It's easy to scale subsymbolic AI. It's based on big data, which is good and bad. These days we have a lot of big data, but obviously you need to have big data to train these systems. And symbolic AI, I don't need to have data at all. I can train the system, or can set up the system in that regard. I don't train it. I can set up. In the subsymbolic way, I need to have training data, good training data, obviously. It has a connection to neuroscience, the deep learning, the neural network side of it, for sure, in the subsymbolic part. And it's better for perceptual things. So, self-driving cars, obviously, language processing are typical examples for that. So if you want to get a better intuition about symbolic AI, I would like to point you out to Swish. Symbolic AI, one of the applications or one of the programming languages that you can use to program symbolic AI is actually Prolog. And this is Prolog. What we have here is I loaded one of the examples. It's actually a movie example. So what we are doing is we are teaching the system now about facts. We are saying there are movies called American Beauty. This is the year it was done. Then you have actors and actresses and directors. And, then we say which actor was in which movie. So we are teaching the system here facts of the world, okay? So what we then can do is we can ask the system on these facts, and here are some asks that you can do. We can ask, for example, which film were these two actors playing together? Okay, so let's do this. We are just bringing it here. So we are asking the question, which film was the actor John Goodman and the actor Jeff Bridges? Let's run this. And it says, hey, it was The Big Lebowski. So with this, we are actually, so to say, querying our system. We are asking the system on combining facts. The system did not know the fact that these two guys were together. The system was combining facts to find out that these guys were working together as actors in one film. The first thing you kind of see here is like, feels a bit like SQL, huh? And that is true. It's a declarative way of doing this. You're describing what kind of result you want to have. You don't describe how to stitch together this result. You're describing the result that you would like to have out of this. So this is a fine example of symbolic AI. And how to use symbolic AI. And I would like to invite you, have a have a click on this thing, look around, see how it works. It's quite nice and quite instructive. Okay, coming back to our refresher. Next, ontologies. We will talk about ontologies later on, and ontology is an interesting beast. It's a bit of a philosophical term, and it describes the structure that you give to a body of knowledge. Okay, so you have a body of knowledge, and you're structuring this body of knowledge, and with this structure, you can start, number one, to use this in symbolic AI, because now you have the structure, you know how to structure this body within symbolic AI. But you also can start to argue, to reason over that thing. You can apply the ontology on different elements of this structure, or different entities of this structure, and see how this fits in, and then argue over things. Okay, to make this also a bit more intuitive, let us look into this. So this is an ontology viewer, and web ontology viewer, and what I did was I loaded an ontology in here that is actually a code ontology. It's about object-oriented programming and how this looks like. So, and when we dive into this, we see there are statements. There's control flow, there's a loop statement, for statement, expressions, code elements, there are variables and executables and stuff like this. And you can see the relationship between them if you are drilling down a bit, So let's see. A try statement has resource of local variable, for example. A catch block, catch formal is related to class in that regard. You have complex types, and there's an enum that is a subclass of a complex type and stuff like this. Here you have types, you have the type that might be a primitive type. So if we open the primitive types, there are the typical short float byte and stuff like this. So with this, what we are trying to do here is we're trying to kind of set up a system that helps us to structure, in this case, object-oriented programming into a body of knowledge, and it gives us the opportunity to find relationships between these different elements. This is extremely interesting in the field of static code analysis, as it helps us to apply these ontologies, by using these ontologies, applying them onto your code base, onto your application, to identify similarities between elements, and to identify like the patterns that we are searching for, and to highlight these patterns. So this is so to say, the idea behind ontologies. And again, I would like to invite you, go to this ontology viewer, the web viewer for ontologies, upload an ontology and play around with it and see how these things are working out, and how these structures work accordingly. Okay, so with this, we did the refresher, and let us dive now into static program analysis and see from the lowest complexity level to the higher complexity levels how this works out. So what we will do is we will follow, as I said, the complexity levels. We start with a shallow analysis, and we go deeper and deeper into these analyses. And as you can imagine, there's this cost curve attached to it. On the one side, we have the quality. The quality goes up, the recall goes up. You get better insights of your applications if you use the deeper and deeper analysis. On the other side, we have the performance pain. We have the performance cost that we have to pay, which means time and memory that we have to, so to say, invest to get the better results. So this will be our, so to say, guideline from shallow to deep. Let's start with the most shallow ones. And the most shallow ones are actually starting to treat code as text. Okay, so I have the source code file. The source code is a text file. And now a lot of people had the idea, hey, we have this machine learning that works so nice on human language. it should also work on source code, right? And it kind of does. There is a lot of things you can actually do with a simple grep. So the C++ persons amongst you will remember that there are some functions that you should not touch. The str functions, str copy, and the like. So what you can do is you can use a simple grep, and you can say, hey, find me the instances in my source code where str copy is used, and if so, flag it, because we shouldn't use it. So that is already quite powerful. There was actually a tool coming out which is called the Microsoft Application Inspector that does exactly this. It literally searches for API calls on security or I/O or whatever relevant APIs, and it kind of gives you a feedback. You see the screen clipping up there. And it says, hey, your application is using security-related API calls or something like this, and this is helpful. It's already really nice and can really help. My last example is according to leaked secrets, authentication tokens. You can search for elements in your source code that have a certain entropy, that have a certain setup, like a certain regular expression, that makes it a typical Amazon Web Services secret that you are leaking there. And there are so many of these secrets, and I have to admit it happens to me from time to time. There are so many secrets you leak up to GitHub because it's part of your little development environment, and your git ignore file is not set up well enough, and damn, it's up on GitHub now and viewable for the public. And that is quite easy to do. It's not really understanding the semantics of your code, okay? It's a pure syntactical thing to look at, but it's already very, very helpful. So don't underestimate these tools, and there are quite a lot of them out there. Application Inspector is one of them. There are some machine learning tools out there that are quite helpful in a way, but yeah, so this is the most shallow, so to say, scan that we can do and tool that we can use. Now, moving up a bit, we are getting into the linting world. So what we are doing now is we are dissecting the application by using an alternative representation of the application. So we are going into looking into the application not longer from a text perspective, but now we are looking into it as a graph. So the typical thing you're using there is lint is a very typical tool in that regard. I have ESLint here as an example. And there are other tools, especially PMD is one of these tools that are used in the Java world here. And what can you do with this is, let me make an example here. So there's a rule in PMD that says use equals to compare strings. And it says, hey, if you're saying if com equals end, as a string, that is actually a bad thing to do. You shouldn't do it. You should use the equals method as shown in the green section. Yep, that's very helpful. That goes already beyond the pure text scanning in a way, because you could not simply scan for equal signs. You need to have a deeper understanding. Otherwise, false positives would fall on you as crazy. So this is what PMD is doing. But there are limitations to this, and one of the limitations, for example, is this one. So here, it is no longer easily understandable that we are comparing two strings to each other, because they are camouflaged in a way by getting string, by calling functions. We would now need to understand that there's a function called toLowerCase that is in the string class, and it's actually returning a string again, and you need to have a deeper understanding of this. The last time I showed this, somebody in the audience said, I think PMD does better than this, it's this, I don't know if this is still true. So let me show you what I mean with this, So this is the website of PMD, and they nicely listed all of these rule sets, and this is the use equals to compare string. Yeah, this is exactly what we just did. So how does this work? If you're looking here at exactly what we are using, equal or not equal to compare strings. How does this work? It's actually an XPath query over an XML representation of your code. So it translates your code into an XML graph, if you want to put it this way, and then uses XPath as a query language on top of that. And what it does says, it looks into the suffixes and the postfixes to find the strings. So it would find this one as we just had it, and would say, hey, you should do rather this one. What it cannot do with this is it cannot find the construction that I just showed you, because it doesn't fall into this kind of search pattern anymore. So what we see here is the limitation. It doesn't follow the real typing and stuff like this. It has these limitations by using the XPath expression as it has here. Okay, so do use these tools, don't get me wrong, but also be aware that there are limitations of these tools. Okay, these tools can look so deep into the code. Going back to what we said in the beginning, with the text-oriented tools, obviously the text-oriented tools, they have no understanding of your semantics whatsoever. Here we are even a bit in the semantics. So the text-oriented tools, they cannot argue on these things. So there are even less errors that these guys can find. Okay, makes sense? Good. Next. The next now is, if we're going even deeper, there's a tool called error-prone. And error-prone is actually, doing the next step that I just said. It's setting up a symbol table. It starts to resolve names. It does type propagation. It starts with the data flow analysis. So error-prone is actually a step deeper into finding types of errors that we just had. So, for example, error-prone has this null ternary rule where it says, hey, you would give back a null in certain cases, certain instances. And it would flag this because it would understand that you are doing like you're giving back a type null, you're giving back type null, which might not be what you want to have in that regard. It still is limited, for example, to this. It still wouldn't kind of understand that y is actually a null. It would go there and say, y is an integer. Okay, so this is a valid integer. Yeah, but the integer has a value now, and the value is null. So you're still ending up in the same situation as we had before, but it wouldn't understand it. It would understand, hey, y is an integer is valid, we're fine. So that is the issue with this. Even further down the road, it would not understand this one, for example, because integer y is again an integer, but again, this is a function now, and this function might resolve into a null function, a null value for y. So here again, it would need to understand what comes out of this function. It need to understand, or it need to analyze this function first, and then have a table of elements or of possible results out of that function. Here is the limitation of this. Okay, so that it would not be found. We can go even a step deeper, and there's a tool from Facebook, actually. It's called Facebook Infer. And this does interprocedural steps now. So the problem I just showed you with the function call that might result in a null, this is now something where infer comes into play. And infer kind of jumps in between or follows the flow of your application through the application, through the source code. So how does this look like? Here's a concrete example. I actually have it from the Infer website, and it's it was production code. I guess it's no longer production code, but it was production code from the search engine DuckDuckGo. And what you see here is we are entering this function feed item selected here. And feed item selected calls the select feed by ID function. So if we are going into select feed by ID, you're seeing that we are setting we're setting like the local variables. We're initializing them with null value. So out is null, C is null, and then we are getting into this try here, and we're doing a database query. Okay. Now imagine that this database query comes back with an empty set. Okay, so the database query is a valid query. It executed accordingly. Database was available. Everything is fine, but there was simply an empty set. Okay, there was no result. There's nothing to talk about here now. What would happen with the move first that we have here is it would actually say it would fail. Okay, it would the move first would give us a false because there is no first. There is none. So and it says if move first, it would go in here, but our move first, is failing. So it doesn't change the out in that regard. It also, it doesn't need to kind of get into an error condition or something like this. So the close is also a question mark, if we call it. But what we don't do here is we are not writing something to out. Okay, so out will stay on the null value. Okay, Al will be null. It will fall down here. It will return a null value. Okay, so the simple fact, query empty, set comes back, return will be null. Now with this null is then assigned to feed object. Okay, so in this case, feed object is null. What happens next is we are calling a function called feed item selected, and we are putting feed object into that. We are calling this now feed item selected, so feed object is null. We are going through this, and here we are doing a null dereference. Okay, so here we're using a null value, we are calling get URL on null, and there goes our application. First question. I would say this is hard. It's even the same file, but it's hard to understand the implications that you have here. If you did this, you wouldn't expect this to be null, and there it goes. Okay. Another thing is obviously it's the null value is assigned to several variables and is handed over and stuff like this. So the static code analysis literally needs to keep track on the null value propagating through your application, being assigned to different parameters, and la 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 la. And the third thing that I want to highlight here is that is the difference between static program analysis and dynamic program analysis. Okay, in the dynamic program analysis, if I want to catch this bug, I have to come up with a database setup, an environment setup, where literally the query here results in an empty set. Then I can find this bug. If my environment is set up in a way that it doesn't cater for empty set for whatever reason, but then the real world caters for the empty set, I have no chance on this planet to find this problem with the dynamic analysis. The static analysis argues from a different perspective. The static analysis argues from, is it theoretically possible that we have a null value here? And if it's theoretically possible, it is part of the analysis that the static analysis does, and it finds the bug. So you see the difference here. And I think it's a nice example in that regard. It's also quite a complex one. But it's a nice example in that regard. Okay, what you also can see here, syntactically, everything's super, right? Syntactically, there is no problem with this. We can compile it, everything is fine. Semantically, we can argue now that probably our developer didn't want to have the situation that this feed object becomes null. Okay, the developer intention, or the semantic behind it, the meaning was, I expect this not to be null, okay? But it's not mentioned somewhere, right? So the language doesn't force you to be so explicit on that, okay? Another interesting observation in this code. So what I can do now from a language perspective is I can force you into be more specific, more semantic. Okay, so if you think about what happened with C++, having weak pointers and this stuff, it forces you in being more semantic about the usage of your pointers in that regard. There is a project in Java that wants to go in this direction. This is from the company called Uber. It's a tool called Nullaway. And what Nullaway does is it uses your Java code. So up here we have the typical Java code. And here we see that the function, the object x, is not defined in a way. It might be a null, but if we're using a null in here, it might explode around us. Okay, so we would do a null dereference, just in the case we had before. What we do with Uber Nullaway is that we're literally annotating it. We are setting not null here. We are saying, hey, we want x not to be null, because we don't handle the case that x is null. What Uber's Nullaway then does is it does a data flow analysis. It literally analyzes the source code and says, is there any way, that this parameter can become null? As we just said or just seen in the example, in the previous slide example, it was theoretically possible. And this would be detected here. So here, this application would run, log null, we would call it, and it would make a null dereference. Here, we would actually get an error from Nullaway telling us, nah, you want to have this x being null, but actually it's not allowed to be null. So in that regard, we cannot accept this, and it would give you a kind of a feedback. So what we do here is, as a developer, we are more semantic, okay? We are describing our intention better by saying it cannot be null. And we're giving the framework the chance to find these kinds of bugs with this. The downside to it is, obviously, it's more work, okay? You need to annotate all of this. And the other thing is, we are all humans, okay? So the point is the annotation needs to be correct, because now we're based on the annotation again. So these are the two downsides that are with this. But it's an interesting project, Nullaway. Have a look at it. Because it enables us to be more semantic in Java. What we also can do is we can, so to say, try to argue without the semantic, okay? And we might end up in a situation that we point out a false positive, You might have a null dereference in there, but I'm absolutely sure, this database table will never, ever give me an empty set. So because I know it will never, ever be an empty set, I know more than any static program analysis can know. But the static program analysis will argue, there's the theoretical opportunity of being there. So that is the two trade-offs that we have to do there. Okay, let us dig deeper. And the point that I wanted to make with this kind of a set of tools that there are is, number one, there are a lot of these tools, okay? So you see on the left side, you see the the commercial tools. On the right side, you see the open source tools, and there are lots of these tools, and we should use them, obviously. They all have their pros and cons. As you have seen, they have their limitations in a way. I want to make you aware on IntelliJ. I guess most Java developers use IntelliJ. At least whenever I was asking, everybody was using IntelliJ. IntelliJ comes with a variety of built-in tools that are actually a collection of a lot of open source tools, and they do a lot. So make sure you check the static code analysis in IntelliJ also. And have a look at it. It's a treasure trove. It's already there. You have it. You can use it. And as you see, there's more. One thing I didn't mention here is actually DeepCode. And what I now would like to do is I would like to give you a kind of an introduction into DeepCode and how we differentiate in this regard, where we are on the complexity scale, how we do things, what makes us a bit, so to say, different in that regard. What DeepCode does, and like the most advanced tools are doing, is we're looking into constraint-based analysis. Which is currently like the so to say the highest class of these tools that you have there. These constraints are literally the rules, and you have seen Prolog. You know, we are not using Prolog. We are using a tool called Datalog, and with a kind of our own twist with it. In a way, it's like the same makeup. So we have these rules. We're using this language, and we are building now a graph representation of your application, and we are then using these rule sets on this graph representation of your application to come up with our suggestions. And here, if you want to dig deeper into what this means and how all of this works and stuff like this, here's a paper that you can follow that gives you a very deep insight into it. Be warned, it's computer science at its best, but that is the way if you want to dig deeper. So we started off with these limitations. Remember, that was one of the slides we had, performance and that stuff. Obviously, as DeepCode, we were in the same situation, and we wanted to be on the top notch on the static program analysis. So all of these apply to us. Now, the ideas that we have, how to solve these, I want to give you a bit of insight in how we are doing this. And I guess the rest of the industry is trying to follow us in that regard. First, starting off with performance. What we did performance-wise was we built it all ourselves. We have it in-house made. We had a look into the way that these Datalog solvers, again, Datalog is a kind of a subset of Prolog, which is the symbolic AI part on which we are running here. We had a look at it, we optimized it, and we are about to publish the data that we kind of got out of it. We want to make sure that it's really profound, and so we are working with some industry and open source projects to have a very good data set where we can show how our solver works versus the default solver in the industry and open source. And I can say performance-wise, we are orders of magnitude faster and use less memory than what you typically find in the industry. So I think this is something that is enormously important for us. Out of two aspects. The aspect one is, obviously you want the tool to run very quickly, to be very fast. Aspect two is, think about the sub-symbolic AI, think about the machine learning part of it. If you want to use machine learning, you have to use lots of training data. The training data needs to be generated, needs to be made up for you in a way. Again, performance. You know, if you want to use huge sets of training data, you need to have a good performance of the system to generate the huge sets of training data. Okay, so you get that point. Because we're using semi-supervised learning, and there we got it with a machine learning. What we can do with the performance side of it is we can generate a lot of training data for our system. And what we're doing then is we are trying to use a combination out of a person and a machine learning system to generate the rules that we have. So we are looking into the source code. We are able to see not only the current version, but also the changes in between the versions of large amount of source codes in the open source community. We are analyzing why changes happened, and then we are trying to find, so to say, patterns in there that are of interest for us. As soon as we find these patterns, we're involving a human being and asking, okay, is this something that should be of interest to us? If yes, we can hunt for more patterns. We can literally say, if we apply the rule that we found out now to more code, what do we get out of this? Is this good? Is this bad? Again, we are working here with a combination out of machine learning and a human being giving us guidance on how where the machine should go. And the other part that is quite interesting on our side here is we are working on a very high abstraction layer. So the point that we have here is we're not, as you have seen, like in the PMD case with the rule set being on X path, where we very explicitly are looking for the double quotes in that regard. What we are doing is we are abstracting away from it ontologies. We're abstracting away from it so that we can literally say, hey, if this API function here is actually a source of malicious data, okay, so of data that needs to be cleaned before we can use it. What typical flows do we see in the enormous amount of source code that is out there? What typical flows do we see connected to this function? Where does this data flow? And then we can find out, okay, so the data flows through these functions that are sanitation functions, maybe, to this function, which is a sink where we have a database activity or something like this. With this, we can automatically find out which one is a sanitation function, which one is a sink function. Now we can look into the sanitation and say, hey, yeah, actually, it's a good sanitation. Where does this sanitation is being used elsewhere? And with this, we find more sources of data that are used in conjunction with the sanitation function. And we find more sinks of data where the data flows out of the sanitation function. With this, we can automatically find more and more instances where, for example, this taint analysis that I just described here can be used. We don't need a human being for that, so we can literally use enormous amounts of source code, changes that were done in source code for the system to learn, to train new API functions without us explicitly saying, wow, this is a new API function here. So, and this is the way our system works and our system scales. And we are overcoming this kind of a linearity of the rule sets that we have. We are overcoming the enormous amount of APIs that are there and stuff like this. We are overcoming the polyglot part of it because we are working with ontologies again. So we are abstracting away from the use of your language into a more abstract way of using languages. That helps us to apply rules on a wider variety of languages and much, much, much more. Again, ontologies also help us on the expressiveness of things. Because ontologies help us to argue. We can literally argue backwards. And use the rule sets that we have, and we can say, hey, because we found this and that in conjunctions with that, and I will show this to you in a second, this is why we come up with this problem here. And we can be much, much more expressive and give you also help in a way how to overcome the problem. How do we get help? The thing what we are doing is we are literally looking for examples in open source where the problem existed and the problem was addressed with a pull request. And we are looking into how did this pull request actually address this problem. And then we are showing you the pull request that addressed the problem. So that you can literally see, this guy had the same issue, and by applying this pull request here, the issue was gone. So that is the way we are kind of helping you to better understand the argumentation, why the system comes up with this issue, and also to help you to remedy the issue by using what the open source community kind of learned already about it. So our whole pipeline that we're using looks kind of this. We're using DeepCode, GitHub, GitLab, Bitbucket. We're using vast amount of open source, 200,000 repos. Not only the actual version, but also the history of these things. So how did they change over time to address obvious problems that we have? We are providing an input mechanism for various languages: Python, Java, JavaScript, TypeScript, and we are using these trees that we are generating out of this abstract syntax tree, but also the event tree that I showed you before. We are using our own solving mechanism. Here we have this prolog / data log element that comes in here. We're using this to get the semantic facts out of this. And now you know what I mean with semantics. It's no longer about the pure syntax. It's now we are trying to argue about the meaning of it. The reason why you did certain things the way you did. And then we are comparing the things to each other. Okay, so your application would literally flow through the same pipeline. We're using this pipeline to go over DeepCode and to help us setting up this knowledge base. Now you know what the knowledge base is, because it's the set of rules that we are using here. And your application runs through the same pipeline against the knowledge base, and we provide you what we learned from the DeepCode that we kind of used for training beforehand. Okay, so this is the way we're doing this. What I would like to do now is let's jump into an example. And what I did here is I actually used the JDK, OpenJDK. I took OpenJDK 14 and I took parts of it out. It normally runs within seconds. Okay, it's hard to show here because we're also using a caching algorithm underneath it. And I would like to invite you, try it yourself. Use a decent sized code base that you have and run the scan over it. So what you need to do for doing this is you're going to the website DeepCode AI. You can log in here, or if you're already logged in, you can go to my dashboard, and here you see your repos that are, in my perspective, here now on github.com. And what I did was, somewhere in here, I have the JDK 14 parts. I kind of took some parts of JDK 14, and you see it has critical warnings here. And this is actually, if I go on audit here, you're seeing it's loading the data. It already scanned it, so I don't want to fake this and say we're much faster than we are actually doing. Do it yourself. Just try it yourself. As you can see, we had 9,340 files in Java were scanned here, so it's quite significant what we're doing, and we have an analysis time of a bit more than a quarter of a second. So this is, these are the files that we have here, and this is the time that it needed to be analyzed. Yeah, mostly loading the data into the machine and generating the view of the review is actually the most time-consuming part of it. So I was browsing through this a bit, and I found this one here. And what it does is it says this issue was fixed by 60 projects. And now you know what I mean by 60 projects. We found this in the history of 60 projects that we were scanning out of GitHub and the others to be fixed. Okay, so this is what we mean with 60 projects. And you see now, this is the reasoning that comes out of the engine. It says unsanitized input flows from a data source, from a remote resource, and is used in an URL to perform a request in an open connection. This may result in a server-side request forgery vulnerability. Okay, so this is the argumentation that comes out of the rule set. Now we can argue even deeper. We can say, hey, flows remote data. Okay, so what is the remote data source? It's here. It's this header file. Get header field. Okay, so it's the remote data source. It's a header file that is obviously provided by the request header, and so this is the source that we have. It flows. You see, it flows into this. So it has it goes through several so to say, iterations or assignments or stuff like this throughout your application. It can be wherever need be. You know, we are doing a data flow analysis, so we know where it came from, we know where it goes to. And it kind of argues now over the open connection that is then used down here. You know, so the URL open connection. So now the question is, okay, you know, server-side request forgery, maybe you've never heard of this. How can I get more information? And here is more information. So if you click on this, this is actually the OWASP, so to say, what is server-side request forgery? This is the background of all of it. How does this work? What is the, so to say, the issue behind it? What we also do is, as I said, we saw this in 60 projects. And here we have a selection of projects and how they, so to say, reacted on this. So how did they have it? How did they, what did they change on it? And you have maybe similar suggestions. You know, it doesn't, this one here doesn't only happen once, it happens on other occasions with similar suggestions, okay? Where it might have like a different source, for example. And now you know what I mean with different suggestions, because since we are working on a higher abstraction layer, we're working with ontologies. The point here is that it might have a different source function, or it might have a different sync function or something like this. But for us, it's the same, rule that is kind of firing here, because we learned different functions that might be used in that regard. And the last point here is you can give us feedback on this one. So if you are saying, hey, no, not the right thing, okay? You have two options if you're saying it's not the right thing. So number one is you can say, I ignore this here. You know, for example, if you have test code, and you very often have a pseudo password in test code, a hard encoded password in test code. Happens, you know, it's okay, it's only test code. Still, our system will flag it and it will say, hey, you should not hard encode passwords in your test code. So what you can do is you can say, hey, ignore this. Okay, it's just test code. Let me have this here. So it will help you to kind of steer the system, ignoring it. Again, semantics. You know, you help us to understand that no, it's not a real password in that regard. Or if it is a real false positive, you're saying, nah, you know, this is not the real thing here. You are misinterpreting things. You can give us feedback here. So type the feedback in here, give us a judgment, and send it off. It will normally take us a day to come back to you and to give you a report on. Was this a real problem on our side? What did we do to change it? It normally takes us a day to do that. So we are very fast in turnaround if there is something that really needs to be addressed. So this is the way that you can, so to say, interact with us in this regard. And this is the way that, that this works. Okay, coming back to this. What are the do's and don'ts that I promised you? Success measure should be bug fixed and not issues identified. And this is something that Google learned. There's a, down here I have the resource. Google did a whole study on how static code analysis tools are actually used within Google. And this is actually how they came up with. So one of the learnings is the success measure should be bug fixed and not issues identified. Why this? In Google, there was a special team that was responsible for the static code analysis. And as you can imagine, they were really proud in identifying bugs. The problem with it was nobody fixed them. So the more bugs, the less motivated the developers got. Not a good way. Both teams, all teams need to be focusing only on bug fixed. Shift left is good, and we talked about it in the beginning, you know, pushing the quality down the left side of the process. That's a good thing to do, but be careful. Don't overdo it, because too much shift left hurts. What do I mean with this? if as a developer, I do, for example, test-driven development, I start off with an obviously wrong thing, but I start off with this and then I add tests and it's, again, the test is failing and I move my way forward. If I do this and the static code analysis is kind of eating me alive, I'm doing one line of code that is not production ready yet, but I already get 50,000 warnings and errors and that is actually not helpful. Okay, it's kind of bogging me down. So be aware that it needs to have a certain moment in time when you start with your static code analysis, that it doesn't hinder, but is really helpful in a way. So this is what I mean with shift left is good, but don't overdo it. The more and more you get right in this pipeline, the finer and finer your sieve should get, the more tools you should have. There's this cheese slice model that is famously known from the airlines and from the avionic industry. And what is meant by this is every cheese slice has a hole. Okay, so you know that every slice of cheese has a hole. But if I put cheese slices on top of each other so that the holes cover each other, all of a sudden, if I look through it, the cheese is solid, right? And this is the idea that is with this. Having systems that are on top of each other, that are kind of extending each other is very, very, very helpful in this regard. And the more right you get, the more of these systems you have and the finer the systems should be. Another thing is it needs to be integrated into your development process and the developer workflow, and it's key to do that. If it is not integrated, it's a separate tool and stuff like this, people tend not to use it. They don't call this, they don't use they don't use the feedback they get out of this. So use IDE integration, free from DeepCode. We have Visual Studio Code integration, we have Atom integration. We're working on more integrations. We're also having a command line interface so that you can integrate it into your continuous integration process, for example. Do this. It needs to be part of the process. And last but not least, use the tools on your legacy code bases. Software is never done, okay? Software has the tendency to kind of degrade over time. You should revisit your legacy code base. One of the best practices is doing this like every 6 months, having a run of the libraries, updating all of the libraries, getting them to the latest and greatest, so to address the latest security updates and stuff like this. Run the CI over it, maybe run the CD over it, but keep it updated and keep it running, because these tools are constantly evolving and constantly learning, and so should your code. You should kind of move forward with this. Outlook, what to expect next, what will happen in the future. And the point that I want to make with this slide is, will there be the Clippy of the future? The Clippy that says, hey, looks like you want to do a very impressive piece of code. Let me help you with this. I will do this code for you. And the answer on this is no, it won't. While there will be more intelligent tools, more tools that help you to understand your own code and to understand other people's code, for example, it still will be the brain, the wetware that is a major element of coding things. So we will be more and more helpful in a way. We will understand better the semantics of it. We will better be with the expressiveness. Maybe the tools will even be so far to construct alternative code for you that you can then insert or like slightly change and insert then. It will find examples for unit tests and maybe even generate unit tests. There's a company called DivBlue that are trying to generate unit tests automatically. So that will happen, yeah. The rule scale need to exponentially grow by using machine learning. I think that is also something that is there. We will see more and more a combination of static and dynamic analysis. So for example, our example with the database, maybe we need to look into the database and see, no, actually there is never a null value coming out of this because the database will never result in an empty set. So that would be a dynamic query that we could do. And last but not least, we could even extend this down the route to the runtime. So having the DevOps part also being part of that, that will certainly be something that we will see in the future. So call to action. If you use static program analysis, you're doing the right thing. Revisit your tool stack, optimize your tool stack. I hope there were some tools in here that were new to you and you can use them right away. If you're not using static program analysis, okay, you're amongst friends, we won't tell anybody, but maybe it's time. You should think about your tool stack in that regard. Look into your project, try some tools, see how it works out, what feedback you get out of this and how you can make it actionable for yourself. And as I said, IntelliJ is a good start for the Java developers for sure. But I would also advise you to give us a try from DeepCode, to look into it. It's free. You can simply scan your GitHub repos and see how they behave accordingly. That was my presentation. Thank you very much. We used 1.5 hours exactly as planned. I hope you learned something out of this. Give us feedback, please. Steer us in the right direction and tell me if you want more content like this. What kind of topics do you like to have? Give me feedback and I will react on it. Thank you for being here. See you later.